Alright, so we already talked about density a little bit this semester, and we did Lab 101 at the very beginning of the semester, but we're going to now more formally introduce it. Now, density is the ratio of mass to volume. So this is a Greek letter rho that we're going to use to stand for density. And since density is mass divided by volume, we're going to have units of kilograms per meter cubed. Now, we're used to thinking about density as a constant. So this is a value you can actually look up at the table, but if you look at the table, there's always a note at the bottom that tells you what temperature that density is for, and usually it's room temperature because we tend to write problems meant to be on Earth's surface at room, standard atmospheric pressure, temperature. However, density really isn't a constant value. It has actually a temperature dependence. So you would have seen in the previous video that as you increase the temperature, as we went from a solid, a liquid to a gas, the molecules expanded. So as temperature increases, volume also increases. And because volume is the denominator here, as this one increases, this is going to decrease. So density is actually going to decrease. So density does have a temperature dependence to it. Now, the one exception to this rule is actually water, which is very unfortunate because it's the thing we encounter most in multiple states. And water actually expands when it freezes, so it has to do with how the water molecules arrange themselves into a crystal structure to make a solid. And it actually expands, and that's why during the winter, if water gets into a crack, it then expands and it makes the crack worse. So you definitely don't want to use water as your example in your head for this concept. So there are going to be a table of these densities. They are linked in the constants table in Blackboard, and that's something to provide an exam. And for the most part, we're going to assume that our problems occur at the temperature stated in the constant table. Another new term that we're going to use in this particular topic is pressure. Pressure is force per unit area. And since it's a force per unit area, it's going to be in Newton per meter squared, which is the same thing as a Pascal. So Pascal is another scientist. We don't typically talk about Pascal's principle, though, because it's just one thing too many in this particular subject area. Now, pressure tells us how force is distributed over an area, as the equation defines. And this matters because one example of this is snowshoes. So if you're trying to walk through snow, you sink into the snow. But if you put snowshoes on, that increases the area, because snowshoes are always bigger than your regular shoes. It increases the area over which your weight is being applied. So you don't apply as much pressure on the snow and you don't sink in as far, which is spreading the force over a greater surface. The opposite is true if you go to the doctor's office and you get on the scale and you're wearing high heels. The scale assumes that your weight is going to be distributed over an average foot size. But if you're taking all of your weight and putting it into the heel of high heels, it's actually going to apply more pressure to the scale and make your weight look like it's larger than it actually is. So larger surface area with the same force means less pressure. Same force on a smaller surface area means more pressure. And so how that force is distributed actually matters when it comes to perceiving pressure. Another example of this is laying on a bed of nails. If you step on a nail, you normally have to go to the emergency room. However, someone can lay on a bed of nails because they're distributing all of their weight across a larger surface area of nails, not on a single tiny point of a nail.